So good morning, team, and welcome to our Monty-Cat conference. We had a little bit change of schedule, and we were lucky enough to have Dragos come join us for our Monty-Cat conference. Dragos works with ASAHI, and I really do think ASAHI do the best coronary wires that are out there. And so he's going to be giving us a really comprehensive overview of Guidewire technology and design, how we can use Guidewires better in our practice. For the general fellows and some of our other colleagues who join, this is going to be very technical, so I apologize in the beginning. You know, it's more of interest to people who are using coronary wires and intervention, but obviously please join, but I won't be offended if you find it too technical and you want to start with your rounds and so on. But for those of you who are interested, I think this is going to be a great talk. Go ahead, Dragos.
Thank you so much, Dr. Lateeb. So as Dr. Lateeb said, my name is Dragos. I do work with ASAHI, and I'm here to talk to you about guide wires. You know, stents, they come and go, they change. We went from bare metal to bioresorbable now. That's on the forefront in the US anyway. Atherectomy systems will change on you. Imaging systems will change, but the one constant that will remain there in your careers is the guide wire. So I feel like this lecture is a good foundation and we can build upon that in the future. So why is the PTCA guide wire the most important device in your arsenal? And feel free to jump in at any time if you want to participate on this presentation. I don't mind if it's back and forth and it's kind of an open dialogue. Obviously, if you can't cross with a PTCA guidewire, you can't finish your procedure. You can't get your procedure started, to be honest. You can't deliver stents, you can't deliver balloons, you can't deliver orbital atherectomy, rotational atherectomy, any kind of imaging modality, anything like that. So we need to cross in order to deliver anything. How many PTCA guidewires does everyone here think are on the market? And feel free to throw out some numbers in the chat.
What about 50? Maybe
a little
100?
More.
100?
Keep going.
Oh, really?
Yeah.
It shows, you know, the problem is most of us use only 5 wires.
That's the problem. Everyone has those 5, they're 5 to 10 maybe go-to wires if they do CTOs, right?
Right, right.
So it's over 300 just in the coronary space. Here's some guide wires you might be familiar with. You know, you have the Ultimate Brothers family, the Gaia family. There's a lot of families and then subsets within those families. You have that Sentai family from Boston, the Pilot family from Abbott, the Miracle family that we have, the Xion family. So the Confianza family, the Fielder family. So there's a lot, quite a few wires. So why so many? Well, to kind of put an analogy and kind of bring it more into perspective, there's a lot of cars on the market too. There's more than 300 different cars on the market. Why are you choosing the certain car that you chose? Well, it's a combination of the feature sets offered and how the user experience is in the terms of you applying those feature sets to your needs. For instance, if you need to cross this muddy terrain, yeah, you can do it in that nice Ferrari or that station wagon, but you're going to do it most efficiently with those aggressive tires and high power. However, if you need to complete a race circuit as quick as possible, that high power isn't as important as low weight and good handling. If we need to take the kids to school, yeah, it'd be nice if we take them in a Ferrari, but it'd be a lot more efficient if we take them in a station wagon. You know, there's some metaphors to be said about maybe this can be alluded to support in a wire, and the speed can talk about maybe a very lubricious coating, and here with the aggressive tires we can talk about a high tip load, right? So those are the feature sets we can talk about in guide wires. So what's in a wire? There are 4 basic parts of wire that affect the feel and function. You have the core, that will determine your tip load and how stiff the wire is distally. You have the coil, which covers the core and gets you to that desired standard coronary diameter of 0.14 thousandths of an inch. There are smaller or larger diameters in some special circumstances. You have the coating that goes on top of the coil. So those are the 4 parameters that will affect the feel and function: tip load, core, coating, coil. And we're going to talk about them. So tip load. When you hear a wire, this is a 0.5 gram wire, this is a 3 gram wire, 12 gram wire, etc. How is that tip load actually measured? Well, first and foremost, you should know that different companies measure tip loads differently. The way ASAHI does it is we take a guided gate and stick the last centimeter of the wire through it. And then we deflect it. And the point at which it reaches a 2 millimeter deflection lateral limit is that given tip load. Other companies might have a different deflection limit or a different limit that they keep the wire exposed, maybe 12 millimeters, maybe 15 millimeters. So just something to know, a tip load given from Abbott or Boston or even Terumo or Teleflex isn't going to be the same tip load as an ASAHI tip load. Here are some of the advertised wires. So you have the Cordis ATW. The dark blue ones are going to be ASAHI wires. So these are ASAHI's main workhorse wires, the Xi'an Blue and the Minamo. You have the BMW Universal, the regular BMW, Xi'an Pro Water, Xi'an Black. If you look here, what's interesting, just to talk about a more popular wire, the run-through NS floppy, it is advertised at 1 gram. However, in our tests, it's at 0.5. So that's more equal to the Xi'an Blue 0.5 in Minamos. So something to think about. I know it's annoying, but different companies do have different methods of testing their tip loads. You can also increase tip load 2 other ways mechanically, let's say. So here we have perhaps a Xi'an Black with a 0.8 gram tip load and a Fielder XT in this case, sorry. Both have 0.8. If we put it in a microcatheter, what's going to happen is the microcatheter is going to potentiate that tip load by reducing the lateral play, and then you have retrograde play reduced because your fingertips are holding that proximal end of the wire. So now that force only has one direction to go. Since it's being blocked laterally, it's going to push antegrade. So your effective tip load will go up to about 3 grams in this situation. Now, it all depends on how far you bring that microcatheter and allow for lateral play. And then if you look here, lesions can also act as tip load potentiators. So if you start wiring your lesion and notice that your wire is becoming more effective, that's probably because you are in a very tight channel and it's preventing lateral play and helping you transmit that force antegrade. Something to think about. You don't necessarily always have to escalate tip load if you can work your way into the lesion with a microcatheter. We can talk about tapered versus non-tapered wires. So like I said, the standard outer diameter is going to be 0.14 thousandths of an inch in most coronary wires. However, we do have some tapered feature sets, which can bring it down as low as 0.009 thousandths of an inch, such as the Fielder XT family or the Confianza family. So the taper matters because it determines penetration force. Penetration force is not the same as tip load. For instance, here we have a Confianza Pro with a 12 gram tip load wire, and a Miracle Brothers, that's also a 12 gram tip load wire. But you can see much less surface area for that 12 grams to push down with a Confianza versus a Miracle. Think of it like cardiac output, heart rate times stroke volume. You can raise one or the other to increase cardiac output, or both. Cores. Cores can determine a wire's support and also its torqueability. All wires are going to be exclusively one of two materials. They're either stainless steel or nitinol, and they have trade-offs. For instance, stainless steel cores tend to be more torqueable, but a little bit less durable. Nitinol cores tend to be more durable, but a bit less torqueable. And then depending on how long those cores are can determine the support profile of a wire. You're going to hear this term a lot. What? This wire has a lot of support. Oh, this is a highly supportive wire. And you're going to get different definitions of what people determine support to be defined as. The simple answer is support determines the ratio of full body to degree of taper of the wire. So a highly supportive wire, such as the Grand Slam, is going to have a very long proximal body and then a very short abrupt taper covered by a spring coil. A low support wire but highly flexible wire is going to have a long drawn out taper covered by a spring coil. Obviously, highly supportive wires are going to help deliver devices, and they're going to have a certain degree of arterial straightening, let's say. So a shorter taper means more support. A longer taper means more flexibility. Again, there's this theme of give and take. So whenever you increase the function of one part of the parameter, you lose something else. So the more support you have, the less flexibility. And then you can see, for instance, in some kind of tortuosity, a highly supportive wire is going to straighten out that tortuosity. It's not going to want to take those bends. Whereas a highly flexible wire with not so much support is going to be more compliant to those bends. When is this important? Well, tortuosity. If you're in very extreme cases of tortuosity, you want to avoid these highly supportive wires, especially in retrograde cases. Sometimes you want to straighten out that artery to help deliver more bulky devices past bends where they normally wouldn't go past. The spring coil. So the spring coil serves two purposes. It helps cover that tapered core and bring you out to that desired 0.14 thousandths of an inch diameter. Without the spring coil, you'd have a very sharp core, and maybe this could happen. Coatings goes a little bit deeper than hydrophilic and hydrophobic. And again, there's that theme of give and receive, right? As you go more hydrophobic, you get more tactile feel. As you go more lubricious, you get less tactile feel. And that's more hydrophilic. Lubricious, hydrophilic, I'm going to use those terms interchangeably. And there are two in between.
So, Dragos, sorry, this is something that confuses me all the time. A polymer jacket wire is more hydrophilic than a hydrophilic wire?
Correct. So I'll get into that in a little bit, why it's more hydrophilic than a hydrophilic wire.
Okay. And the reason I ask that is in the past, we would say that, very hydrophilic wires can cause wire perforations much easier. Yet my experience with polymer jacket wires is we haven't seen that as much as we did, say, with the old pilot wires, right? That were or the whisper wires that were very hydrophilic. Is there explanation for that, or is that just my experience?
So the pilot wires and the whisper wires are all polymer jacketed wires.
Okay. Okay. So what's a typical hydrophilic wire then, when you say hydrophilic? Yeah.
Typical hydrophilic wire is going to be something like the BMW, the Turbo run through. Those are just typically hydrophilic wires. There's no jacket on them.
Okay.
The Gaia family is just hydrophilic. It's not jacketed. The Confianza is hydrophilic, but it's kind of more of a hybrid. It's hydrophilic with an uncoated tip. So once you do interact with that lesion cap, you don't slide off of it.
Okay, thank you.
For instance, here we have a Miracle Brothers, which is purely hydrophobic. Then you have a Xi'an, which is purely hydrophilic, not to be confused with the Xi'an Blue. Then you have the Xi'an Black, which is polymer jacket hydrophilic. And hydrophobic coating will be wax-like when wet. It's going to give you the most tactile feedback. You will feel it in your fingertips, provided you're not using a torquer. If you're using a torquer, you're going to get, there's a degree of separation there for your transmission of tactile feedback. Hydrophilic coatings will become gel-like when wet, and I'm sure you felt that when you pulled the wire out of the body. The wire is very sticky and slippery. Hybrid coatings now, kind of that in-between of hydrophilic and hydrophobic, such as the Xi'an Blue and Manamo, have a mix. They have that distal end is going to be hydrophobic coating. So for instance, on the Xi'an Blue, it's going to be about 1.5 centimeters. With the Manamo, it's going to be 3 centimeters. And then followed by, depending on the wire, let's say 18.5 centimeters on the Xi'an Blue of a hydrophilic coating for a total length of 20 centimeters. The nice thing about these hybrid coatings is they give you the best of both worlds, truly. When you're interacting with an unknown lesion, let's say, or you already classified it on diagnostic angio as a type A to a type C lesion, you don't need full hydrophilic wires, and you definitely do not need polymer jacketed wires. There are some places that just love to jump to a polymer jacketed wire right away as their workhorse, and I kind of try to instill that you don't need to, you're escalating for no reason. You're using a wire, like Dr. Lateef said, that wire that can perforate, especially, let's say it's an older patient, uncontrolled hypertension, severe tortuosity. He can have intimal micro tears, especially around the lesion. A polymer jacketed wire will find those, and they will get subintimal. Whereas a hybrid wire, more hydrophobic wire, will tend to shy away from those and stay kind of true to that lumen or whatever's left of the lumen with the lesion. Does that make sense?
Yes.
Excellent. So polymer jacket wires will become gel-like and smooth when lubricious. So what's inside a polymer jacket wire? Why is that a different classification of lubricity than just hydrophilic wires? Well, if you look at a close-up magnified view of a spring coil, every wire has a spring coil on it. Spring coils, if you look between them, they have valleys. You have the peak, that is the part of the spring coil, then you have the valley, then the peak, then the valley for the length of the spring coil, whether it's a 10 centimeter spring coil or a 30 centimeter spring coil. Polymer jacket wires is very simple. We spray polymer resin on top of that spring coil, and now we reduce the contact force, the contact surface area, not force, sorry, the contact surface area of the wire with the lesion. So physically, there's less stuff in the lesion that can grab onto those valleys in the wire. So that's why these wires tend to be more lubricious, and that's why they tend to be chosen for calcific lesions or mixed morphological lesions or densely fibrotic lesions where there's a lot of architecture in that lesion that can grab onto those valleys in the spring coil and reduce your and increase resistance. Buckling the wire, destroying the wire, you have to pull out, for instance, like a Pilot 200. I'm sure you've seen plenty of those wires get mangled up, and you might wind up using 5-6 in a case just because of that very dense lesion. The way you'll identify a polymer jacketed wire is that it'll be black, whereas an uncoated wire, by uncoated I mean no polymer resin coating, it could still have a hydrophilic coating, it'll be silver. Always. This is an absolute fact. If you ever see the tip of wire that's black and plasticky, you know it's polymer jacketed wire. Polymer jacketed wire should be used a little bit slower with more intent. So glide your way through the lesion, torque it with purpose, and push forward after. And we'll get into torque just in a little bit. So what's special about ASAHI's guide wires? And they truly are different than conventional guide wires. Well, first we'll talk about ASAHI's 4 core technologies. We have wire drawing, wire forming, resin coating, and torque technology. Wire drawing is as simple as it sounds. ASAHI, one of the only companies that takes pure raw materials, in this case stainless steel, and brings it to the desired finished product. So here, stainless steel gets progressively drawn through these diamond-coated dies that get smaller and smaller diameter that help produce the diameter of that stainless steel wire.
Can you explain what you mean by drawing? I mean, what does that mean?
So literally a thick wire is run through these. If you look at this cross section,
yeah,
you see how the diameter is progressively getting smaller. So the wire, the stainless steel actual fiber is drawn through these holes, and they're encircled with diamond. And this diamond just cuts the wire into progressively smaller diameters until you get to whatever desired core internal diameter you want to reach. Because remember, all cores have certain degrees of taper, whether they start tapering, let's say 28 centimeters proximal to the tip, or maybe 15 centimeters, or maybe 5 centimeters proximal to the tip. So we can draw out that wire depending on how we want that core to taper through these diamond dies. Does that make sense?
That makes sense. Thank you.
Sure. So after we draw those, we can form them and make hypotubes or make braids. We'll get into hypotubes in a little bit, and what do I mean by that? So here's an animation of the drawn wires being put through a machine and forming a hypotube. Why is this important? We'll get into that. So coating technology, we also have our own coating company, and we can put any kind of coating on any wire. We can change coatings based on customer feedback, things like that. We're not reliant on any company. That's really the take-home message. ASAHI does everything from the ground up. And torque technology. Here's a wire going through 2 90-degree bends, and then going through this hole superiorly, and it's able to torque like that. Now, if we're doing this in person, we'd have models out, and you could compare different wires, and you'd see that other branded wires cannot simply do this. They can't point to pretty much any number on a clock face, for instance. You'd see that there'd be some sort of deficiency there, and you'd be having something known as wire whip, where your wire might be at 1 o'clock, you'd be inputting more and more and more in torque. That wire is not moving, and then out of nowhere, it's going to move and jump to 9 o'clock. And here's a illustration, let's say. If you look here proximally, you have the operator input, and before torque technology, you have that lag where it does whip. Whereas with the Xi'an Blue or Manamo, it's going to be as close to one-to-one input to output as possible. Why is that? Well, it's not necessarily just because of these 4 technologies. It's the advent of ASAHI's new Act 1 technology. ACT stands for ASAHI cable tube, those hypo tubes we were talking about earlier through that wire braiding process. To understand this, we need to go into the 2 fundamental archetypes of all wires. So every wire exclusively, every wire you've ever touched was one of these 2 archetypes: a core to tip archetype, shaping ribbon archetype. What is core to tip? Well, as that stainless steel core eventually gets distal enough, you have a joint where it becomes, in this case, nitinol. This black portion is going to be nitinol. And then the core, now this whole black portion is the core, it's going to reach the tip of the wire. Seeing that it's nitinol, these tips are usually flattened out because nitinol is quite difficult to shape. I'm sure you've all held those stent samples, and you can squeeze them in your hand. They're always going to recoil back to their original shape. Well, the same thing with a nitinol core. So the only way to shape a nitinol core that goes to the tip of the wire is to flatten it out and make it much thinner, much flimsier distally, which reduces durability and torque response. Those are the 2 negatives. And then you're losing that known durability from nitinol just to be able to shape it. A shaping ribbon archetype, again, you have the core, which there's a joint where it is bound to that nitinol, and it doesn't quite reach the tip, right? So they stop the core a few centimeters to millimeters, depending on the wire, and then they weld a piece of stainless steel shaping ribbon onto that tip. So now this is a BMW. So this first core to tip wire was your classical run through. The shaping ribbon wire is your classical BMW, and I'm sure you all know that a BMW can easily be shaped. Problem is, it can easily lose its shape too, and now you know why. There's nothing in that core helping you retain that shape. So you might get a really quick shape out of it. That means you can really quickly lose it. Here's a Xi'an Blue or a Manamo wire. Right away, you see that there's no joint between the core and the body of the wire. It's called jointless spring coil technology. The core has long, drawn-out tapers, and you see that it's reinforced in 2 ways. You have multiple stacks of this Act 1. These blue stacks here are the Act 1 technology, the ASAHI cable tubes. Depending on the wire, you might have more stacks. Here, for instance, this is a Xi'an Blue. You'll have 5 stacks of these 6-wire braids. And then the core will go to the tip. However, if you notice, there's almost like there's 2 cores. However, this is actually a 7-wire, very thin braid that gets welded on top of the distal core. So this kind of acts as a shaping ribbon, but as also a tip shape retention tool. So the idea is that these 5 tubes are going to enhance torque response. They're filling up the empty space. Classically, you have all this empty space between the core and the spring coil, the core taper and the spring coil. ASAHI fills up this empty space. The more empty space you have filled, the better your torque transmission. This twist wire finally at the end, this is not a cable tube, it's just a twist wire, it's not hollow. It fills up some empty space, but its main purpose is to help you tip shape retention and tip shape durability so you don't lose that shape once you place it. So when you do shape a Manamo or Xi'an Blue, just remember, for the lack of a better word, there's more stuff inside of this core. And we don't recommend tapping it where you put it through an introducer and kind of just tap it with your fingertips. We recommend combing it with the introducer or include a tool such as in the Manamo where you can actually comb the wire. Less is more when you're combing them. You don't need to aggressively comb them, maybe 2 or 3 passes to get your desired half round shape. If you want to go a little bit more aggressive, give it a 3rd or 4th pass, but you can always add passes, you can't remove. Something to think about. So here's kind of a blown out view of a classical core to tip wire, which is just nitinol core covered by a coil. That's it. So there's 1 wire, 2 wires total if you count that coil. An Act 1 ASAHI wire, like a Xi'an Blue or a Manamo, also a Xi'an or a Xi'an Black or a Gaia, a Suo, a Fielder XTA, Fielder XTR. All those are Act 1 wires. You're going to have a core, you're going to have a 7-wire braid, another 6-wire braid on top of all of that, and then the spring coil. There's 15 total wires in a Xi'an Blue, as opposed to 2 in a standard core-to-tip wire. It's pretty crazy when you think about it. Here's everything put together and an illustration showing everything coming apart and getting put back together. There it is. And obviously, coating of choice on top. This illustration is going to demonstrate that torque response, right? So you have proximal input by the operator, wrist or groin. The wire is going to make multiple bends as it passes through the aorta down into the coronaries. And your input is going to have a mismatch with your output in a low torque wire, let's say. In a wire that has true one-to-one torque, 5 degrees of input is going to be 5 degrees of output. The reason this is important is because you might encounter some frustration when using a true one-to-one torque wire. Let's say you're pushing it down the LAD and you've been accustomed to using wires like Run Through or BMW that don't have one-to-one torque. They truly don't. It's not even close, actually. In order to overcome that deficit, you spin them. You spin them very fast and push forward as you're spinning. If you do that with a high torque wire, it's going to react to that entire input that you're spinning. And you're going to catch every side branch along the way. You're going to catch every septal, every diag along the way. And I've gotten operators who just call me up and get frustrated after using a Xi'an Blue. And I say, well, you got to slow down a little bit. If you see that you're pushing your Xi'an Blue down an LAD and it's catching that D1, pull back a few millimeters, torque it maybe 5 or 10 degrees, and then push it forward again. You'll avoid that D1, and you can just push it forward smoothly without having to spin it anymore. Any kind of branch you catch along the way, pull back and always torque just a little bit. The wire will respond to every input you make. Very important to understand that. It's a whole different way of thinking compared to classical core-to-tip and shaping ribbon guide wires. Here's this model again, but now you actually see the operator's hands. It doesn't seem like much, especially when you don't have the hands-on, but what's happening there, it's really eye-opening when you see it or experience it in person, because other wires simply don't have the ability to do this. And Dr. Latiba, we'll set up a day to come and bring in these models so everyone there can experience this firsthand.
Yeah, no, I think it'll be great, because I think what people are missing here is just seeing that whipping, right? Because I remember the first time someone showed me the difference between a ASAHI wire and a different wire, and when the Xi'ans first came into market many years ago, that was what blew me away, was the fact that you don't have whipping of the distal tip of the wire when you're trying to control it. Absolutely.
Here's the crush test. So this demonstrates the durability of those extra, there's an extra 13 wires inside sitting on top of that core. So what does that help when the tires meet the road, right? When the rubber meets the road? Well, you see here that the operator is pretty much smashing this wire into a plastic, a hard resin plastic, which is harder than any lesion will ever be. And you're maintaining that workhorse shape. That won't happen with another guide wire. You will lose that shape.
So, Dragos, just for the fellows, I'll challenge you a little bit about that. So that's good and bad, right? The fact that it maintains its shape is great.
Mhm.
And so I always tell my fellows that, when you're trying to get through a stent and you see to get to a side branch, you get to a distal lesion and the wire is getting mangled up by the stent, change to a Sion blue, because it's going to maintain its tip, right? And that's great if you know how to control the wire well. The
Yes.
problem is, I don't think there's also a downside to this. So if you a young interventional cardiologist and you're a fellow and you're learning how to use wires, this is not the best wire for your first wire, right? Because the fact that it retains its shape so well means that a new operator, if they go into a plaque or they go subintimal, they often don't notice it because the wire doesn't deform as easily as another wire.
Sure,
And
sure.
just a little bit, we need to be realistic. There could be a downside in the wrong hands.
It has a less tendency to prolapse and kind of, because once if you're experiencing resistance and you see prolapse, chances are you're subintimal, classically speaking, anyway.
Yeah. But for the fellows learning, I still believe that if you use a wire, people often ask me, and we had a long discussion this last weekend at a meeting, me, Bill Lombardi, Bill Nicholson, a whole lot of us, about when you move a wire, how much of it is visual and how much of it is tactile feedback.
Absolutely.
Right?
Yeah.
Because I always remember these amazing Japanese operators coming to work with us when I worked in Milano and teaching us how to use these wires. And I would be surprised when they would say to me, I can feel this plaque is very calcified and I need to change my wire. All right. And so for some people, there is a tactile feedback. I think that tactile feedback is more there when you're not using a torque. The minute you're using a torque, it's hard to say you have tactile feedback.
100%.
But the most important, I think, is the visual feedback. And that's what, for me, it's one of the hardest things to teach fellows because it comes from experience, is watching your tip of your wire, the way it interacts with a lesion or a plaque and the way it crosses a lesion or a plaque.
I agree.
So,
100%.
It's something you guys, for the fellows, you need to think about. It's, with these wires, they do amazing things, but it's also a wire is only as good as the operator and whose hands it's in. Because, you can take an amazing wire and if you don't know how to use it, you could cause damage and not pass a lesion. And you can take the oldest wire in good hands and you can do just about any lesion, right? What we're trying to do with technology, and especially the technology you show, which I love, I use ASAHI in 90% of my cases, is we're trying to level the playing field a little bit, is what I like to think of it as, right? Whereas before, you had to do these very complex lesions, you had to be this phenomenal operator, the Jeff Hartzler of interventional cardiology, right? And what these technologies do is they allow operators who are more junior, maybe don't have Jeff Hartzler's hands, to kind of get to a level where they can take on more difficult and more complex lesions. Yet, so it's, that's why I love technologies, because it levels the playing field. It puts, it lets people who may not have the hands or maybe, we have challenges with how to cross lesions, get to a better level much quicker. Having said that, there's also a price to pay. So you need to know how to use the technology. And that's kind of why I wanted you to go through the technology in such detail today. Anyway, I don't want to stop you, but I just wanted to make the comment that, it also requires, the wire does a lot of the work, but it's only as good as the hands of the operator or the brains of the operator, I would say, because those hands are controlled by someone's brains, and it's you using your brain to use the wire that makes the difference.
Absolutely, you're 100% correct on that. And the beauty of fellowship is you get to try out these wires and really understand the differences between them and see why you should be using a different technology or an older technology to truly understand how much the Xi'an or any kind of Act 1 wire is helping you. So in summary, these are the 4 parameters that affect the feel and function of your wire. It's going to be tip load, your core, coating, and coil. Exclusively, all of these are going to affect the feel and function of any wire you use for the rest of your careers. These 4 parameters are the most important thing to understand. You're never going to have to remember, okay, the run through NS, the Xi'an blue, the fielder. There's so many, there's over 300 guide wires out there. You're probably not going to remember all of those. You will remember a set few for sure, but as long as you understand the wire function, you'll understand how to use it. Go back to that car analogy where you understand the properties and the feature sets in a wire. So if you understand the task of the wire and then understand the properties of the wire, it's going to lead to more procedural success. Whereas if you're playing that wire bingo game and you're not, I like to call it horizontal versus vertical escalation, where you're having a difficult time with a lesion. However, the wire you just pulled the second time has the same properties as the wire you're having an issue with initially. So that's horizontal escalation. You're kind of just pulling based on names that you've heard. Versus if you understand the wire properties, let's say you have a calcific lesion and your Xian blue isn't getting it. Your Xian blue simply cannot get past that calcific morphology. Well, don't go with a run through or something in that workhorse 0.5 gram range. Change something up about the wire. Maybe change the coating. Step up to a polymer jacket. Maybe step up the tip load a little bit. Maybe you need a little more like those aggressive tires. Maybe a little more aggression to push through. Or if it's on a tortuosity, maybe you need something a little more flexible. Go with something with a longer drawn out taper. So it all depends on the task the wire needs to complete. And if you can understand the wire properties, you'll have more success. Think vertically, not horizontally. So wires we covered in today's presentation. We covered workhorse wires, Xian Blue, Manamo. We covered polymer jacketed tapered wires, such as Fielder XT. Highly supportive wires, such as the Grand Slam. Highly flexible wires, such as the ASAHI Xian, not the Xian Blue. And polymer jacketed flexible wires, such as the Xian Black. Funny thing is, these are all sub 1 gram tip load wires. They're not aggressive wires at all in terms of tip load. They just have very different properties. These go from 0.5 grams to 0.8, 0.7, 0.7, and 0.8. So they're all in that same range, but they all serve different functions. That's really the take-home message. Tip load is not the end-all, be-all of a wire. Wires that we'll talk about in a future lecture going to be the Gladius Mongo, the Gaia series, the Suo, the Miracle family, the Confianza family. And if you notice these outlines around each wire, they actually did tell you, it's a ASAHI system anyway. Go back one slide. They tell you the type of coating on that wire. So for instance, this lime circle, this is on the box as well. So I'm not just saying it for the sake of saying it. If you look on the box and it says Xian Blue and has that lime coating around it, that's how you know it's a hybrid coating. If you see a black coating around it, you know it's a full polymer jacket coating. See a red coating around it, you know it's a hydrophobic coating. See a full blue coating around it, you know it's a full hydrophilic coating. And here's black again, Xian Black, you know that's a polymer jacket coating. An interesting one is in the Gaia family and in the Confianza family, where it's kind of a half moon blue outline, let's say, but then it's uncovered. Well, that's because the tip of the Gaia family and Confianza family are uncovered, they're uncoated. And we do that so the lesion, the wire has a less tendency to slide off that lesion cap, because these are very purpose-built wires. One is meant to penetrate caps and steer through a lesion, while the other one is meant to make its own way through a lesion, such as the Gaia 2 or the Gaia 3. And then you have again this RG3 is going to be full hydrophilic. All the field.
Sorry, I missed it again. You said it and I missed it. When the Gaia doesn't have a full all the way around, what does that mean again?
So the Gaia has an uncoated tip.
Ah, okay. Just the tip.
And then the rest of the body, once you leave the tip, is fully hydrophilic. Yep.
Okay.
Same as Confianza.
Okay.
Confianza Pro, sorry. Confianza is just all uncoated. But we don't make that anymore. It's only Pro. But there are some Confianzas out there still floating around. Those are not hydrophilic, just so you know.
And before you would have two wires for externalization. Now it's only RG3?
It's just RG3, correct. That's our only externalization wire. It's 330 centimeters. Yeah.
There was another one, right? But it wasn't made by you? Was it
there's the R350 that's still made by Telefax. It's out there.
By Telefax. Ah, okay. Okay.
Okay. Honestly, and where does the same thing? So whatever you choose, it's fine.
Where does Fielder FC fit into the previous page?
Okay, so if you notice, there is no Fielder FC on here for a reason.
Yeah.
It's an older wire, has older technology. Also fielder, there's 5 fielders, and that's kind of confusing. We have fielder, fielder FC, fielder XT, fielder XTA, XTR. That's 5 different fielders. The regular fielder is a classic, let's say, workhorse polymer jacketed wire, even though I don't like the idea of using a polymer jacketed wire as a workhorse. The fielder FC is a more flexible version of that. We call it fine control. It's just more flexible, has a longer drawn out taper. The reason that's not being advertised anymore is because Xi'an Black has completely replaced it. Those fielders aren't tapered, as opposed to any fielder that has an X in it is going to be tapered, an XT. If it's a fielder or fielder FC, Xi'an Black replaced both of them because Xi'an Black is more torqueable, same gram tip load, 0.8 grams, and it's more flexible too. So
right.
There's no reason.
And I assume also that's the reason you don't talk about Pro Water anymore either, because it's replaced by Xi'an Blue.
Pro Water is 100% replaced by Xi'an Blue and Manamo, of course, which is Asahi's only nitinol wire. It's our first and only nitinol wire. And I know you have a lot of experience with that wire.
Yeah. Okay. Great. So that's awesome. I mean, we need to have you back because I learned so much, and we need to now spend some time learning about, all these other wires that you didn't cover, the CTO wires. So we'll have you back for another session. I'm going to ask the fellows to come on to see if they have any questions. And while they're coming on, there are a few questions from our participants. So the first one, again, thanking you for the talk and asking you to really talk about what are the differences between a Xi'an Blue versus Minamo, your 2 workhorse wires, and when would you choose one over the other?
Absolutely. So the main difference between Xi'an Blue and Minamo, the tip load is the same, 0.5 grams. The coating is a little bit different. So like I said, that they both have a hybrid hydrophilic and hydrophobic coating. So it's a hydrophobic tip. In the Minamo, you have a little bit longer hydrophobic coating. It's going to be 3 centimeters on the tip as opposed to 1.5 centimeters on the tip on Xi'an Blue, but they both get to 20 centimeters total of coating. And then the main reason the Minamo exists is because it's nitinol. It's going to have that nitinol core. However, it's not fully nitinol. It's actually a really interesting hybrid wire. It's going to be a stainless steel body, the part you touch, a nitinol middle core, and then the distal end is going to be round pressed steel instead of pure nitinol going to the tip. So it actually has 2 transition points from steel to nitinol, then back to steel. This is why you're able to maintain that tip shape durability and that torque response out of a nitinol wire, which classically, back to that give and take relationship, nitinol has very poor torque response, very poor. That's the inherent nature of nitinol. And that's how you're getting 1-to-1 torque out of a Minamo, is that we use a hybrid nitinol stainless steel core.
Okay. Does that answer your question, Manav? Because I assume that was from you. Okay, so before I get the next question from the chat, Jesse or Andrea, did you have any questions?
Yeah, so there's a certain scenario that I feel like would teach us a lot about the different components of these wires that I still struggle with a lot, which is basically ostial or proximal calcified stenotic lesions in areas after high angulation. So commonly this would be like ostial or proximal circ lesion that's heavily calcified and stenotic that you're trying to get through after going out at a sharp angle. So if you go with something with a very high tip load, you will have the wire continually prolapse into the LAD or left main. Yep. If you go with something with a polymer coated jacket or hydrophilic, you might not get enough support to go through the calcification, or you might not know where you're tracking off the angulation. So what would your approach be when you're dealing with a scenario like that? And what do you think that could tell us about the functionality of the wires?
So that's an interesting question because I see this quite often in cases. especially when we have plaque shift as well. We're sending a prox LAD and the plaque might shift into a D1, and now you have that severe angulation approach and you have a brand new stenosis there. In my experience, the most success I've seen is with a hybrid coated wire, where you do have that hydrophobic tip followed by a hydrophilic body. We've been in cases just like you're bringing up, where we've thrown everything at it. We've tried Fielder XTs, Fielder XTAs, even Gaia 2s sometimes, outside of that CTO application, Xi'an Blacks, even Gladius Mongos, which are those polymer jacketed, more aggressive tip load wires. And it's always that hybrid technology that helps you, that gives you the tactile feedback, helps you interact with that lesion at that angulation, helps you push through it. That's my recommendation always when I see that scenario from now on. I'm always going to call for a hydrophobic tipped wire with a hydrophilic body. Does that answer your question? Or?
Yeah, I think so. Especially between hydrophilic and hydrophobic, and when you want that, that's a really good point.
And when you're saying you're using a less supportive polymer jacketed wire, it all depends. It all depends on the specific wire itself, because there are some polymer jacketed wires that can be highly supportive. It all depends on how long that taper is, that distal taper. If it has a very short abrupt taper, that's going to be a very supportive polymer jacketed wire. Where, like, for instance, the Gladius Mongo extra support, it's aggressive. It's got a 3 gram tip load. It's polymer jacketed, and it has very high support. So that actually might be if you can't get it with that Xi'an Blue or Manamo hybrid, I would escalate to a Mongo ES to try to get that angulation. Absolutely.
Okay.
Dragos, may I ask a question?
Yes, go ahead, Andrea.
Yeah, thank you for this presentation. I wanted to ask you, there are so many different guide wires with many different characteristics, but in the near future, what do you think guide wires will be? Which characteristic would you develop better, or would you change in the existing guide wires? Because it seems a topic real well studied in the past years.
So just to make sure I understand your question, you're asking what about guide wires is going to pretty much be the future? What technology of guide wires will be the future of guide wires versus
exactly
current technology? Well, I mean, we talked about it. It's the Act 1 technology. It's it's been around for about 7 years or so now. It's slowly being phased into all of our wires. However, there is one more technology that we didn't talk about today that ASAHI exclusively does. It's called X-strand technology. I'm sure you've experienced it with Gaia Next, Dr. Lateef.
Yeah.
Remember how those spring coils we talked about in those blown out views there was one coil that wraps around the core?
Yeah.
X-strand technology, it's going to be between 56 and 72 different wires that wraps around that core. Wow. And that's going to slowly be pushed out to all of our wires. So the Xi'an will eventually have that X-strand technology. All the polymer jacket, the Mongos, the Fielders, all of them eventually will get X-strand technology, from my understanding. And that further potentiates your torque response and your durability. And it's really ASAHI that's doing that. I think Boston Sentai family, they're Samurai, right? That's their workhorse that they're trying to compete with Xi'an Blue at. Well, they don't make that wire. It's another Japanese company in Japan that makes all those Sentai wires, and Boston kind of just distributes them and calls them their own. Interestingly, they're trying to kind of replicate what Xi'an Blue does, but Xi'an Blue is our last decade technology. We're already working on future technology way past what Xi'an Blue is doing.
But so the advantage of this X-strand is just the ability to have one-to-one torque, even when you inside a plaque, for example, because that's really been, for me, what Gaia Next gives me, right, is the fact that I'm crossing a CTO and I'm inside a plaque and I need to change direction, and I now have the one-to-one torqueability available.
So you're getting more torque response when you're in tighter lesions. And also you're getting faster torque response. So torque has two components to it. There is how much torque response, whether it's one-to-one, and how quick that one-to-one is happening. Especially when you're in a lesion, you notice with a Gaia, you torque it, you have to wait a good 10 to 15 seconds for that torque to actually happen on fluoro. That's not fluoro lag or anything, that's just wire torque lag. With X-strand, that's the biggest thing between the old Gaia family and the new Gaia Next family. That torque response is so much faster.
Right.
It's fantastic to experience a Gaia 2 and then a Gaia Next 2 on these CTO models we have. It really makes it much easier. It's like driving a Ferrari from 1985 and a Ferrari from 2020. The handling, let's say, right? The response is just so much faster. The steering.
Right. Right. Dr. Monrad, I hope you're listening, because part of this, the goal of this talk was to convince you to use an ASAHI wire. Okay, I have a couple of last questions from the participants here. So the one was from Dr. Terre saying, do you guys have any data? So we, when doing bifurcations, we routinely jail wires. There's been some data. There's actually a paper from the group in Spain from Manuel Pan, who did a study where he actually looked at all the wires microscopically after pulling a jailed wire and looking at what's happening to the wire, because there were some concerns that with hydrophilic wires you'll strip the hydrophilic coating and leave that in the artery. Does ASAHI have any data on your wires?
So I've never seen any data presented where we talk about any kind of hydrophilic coating or hydrophilic molecules, let's say, being left behind in the coronary.
Well, so that's okay, don't worry. So one, look at the paper by Manuel Pan. He actually shows that polymer jacket wires are the least damaged when you pull them out. So he actually did a study. He looked at them all under a microscope after pulling them out. And so there is some data out there. Then there's another question here for you, Dragos, from Bob, who's asking a question. He goes, if he has a tortuous vessel that he needs to wire, what would you recommend? And from the ASAHI wires, what is the right wire that would give him the ability to go down the tortuosity, but yet be supportive enough to deliver equipment?
Depends on the location. Is it distal tortuosity? Is it proximal tortuosity? If it's proximal to mid tortuosity, Xi'an Blue is going to get you perfect amount of flexibility and torque response and support, because it does have workhorse level support. If you have much more distal tortuosity and it's very, very aggressive, I would actually go Xi'an Black.
Okay. And then, maybe, Bob, you should know that there's also a Xi'an Blue extra support, which we don't have in the United States yet.
Have that.
I keep hoping that will come. That was one of my favorite wires when I worked in Europe, because it gives you the torqueability of the Xi'an Blue, yet it gives you more support. So when you're doing radial interventions and so on, it's a really great workhorse wire. And then Bob also asked, about when he's doing a STEMI, and he has what's essentially a functional occlusion, and you want to be careful with a very stiff wire, how you escalate. Would you escalate straight from field to FC or Minamo first? So I'm not quite sure, Bob, what you mean, but I assume you mean what if you're using something like a Minamo as your workhorse wire and you can't cross, okay, what's your next wire up as far as tip strength and torqueability?
So after a Minamo, so we're talking about 0.5 gram wire. It depends how aggressive you want to escalate. Do you want to escalate by 50%? You can go to Xi'an Black to 0.8 grams, let's say. Do you want to escalate a little harder? You can go to, well, I wouldn't recommend a tapered wire like a Fielder XT.
No, definitely not.
I would actually, believe it or not, I would probably escalate to something like a Pilot 200.
No, okay, so I'm going to stop you there, just because I don't want to give Bob the wrong advice. So, Bob,
you know more than me, though.
Yeah, I would not do that. I wouldn't go to a Pilot 50 or 200 in a STEMI. Please don't. That's not our practice here in Monty or in many places in the world. I think, if you're struggling with your workhorse wire, we say it's a Minamo. I think then, think about a Xi'an Black. think about whether you want to put a microcatheter at the back and still stay with a soft wire because you are in the setting of thrombus rather than a CTO. It's very rare to have to escalate to a more stiffer wire than that. I think I've rarely had to go somewhere like a Miracle 3 because I have a really old occlusion, but that is a very rare circumstance. You used to have a wire, Dragos, which I used to like in Europe. It's still available in Europe, called the ASAHI intermediate, right? And just because, and we used to use it just because it was intermediate. So it was kind of between a workhorse like a Minamo and going to a Miracle. But it's very old technology, so I'm assuming you guys are fading it out.
Yeah, so the ASAHI Soft and the ASAHI Intermediate are pretty much phased out. Interestingly enough, the ASAHI Soft came back last year.
Right. Okay.
And that's in that 1 gram tip load range. And the Intermediate is going to be closer to 2. Yeah.
Intermediate was closer to 2 tip range?
Yeah.
Okay.
Yeah.
So what's in that tip range? If I needed something and I didn't want to go to a Miracle 3, is it what's in between a 1 and 3?
That's really it's lacking, for the lack of a better term.
Okay.
All the tip loads really stop at 1, and then they start again at 3 and up. And that's why I was saying like Pilot 200, Miracle 3, because that's the only thing I could think of that has a higher tip load than what's currently in that workhorse, more aggressive workhorse tip load range. But like you said, a microcatheter is going to bring you to that desired tip load performance a lot better than escalating. Like we covered at the beginning of the lecture. Just think of microcatheter before really escalating.
Right. So one other thing, ASAHI does have an app, which I downloaded recently, and it really takes you through all the different wires, which I think is useful to have. And then what we'll do, Jesse, any last questions from you? Since you are our chip guy.
Well, last Thursday, I actually had a STEMI that was in that same scenario that Bob had discussed, where we were talking about difficult lesions to cross during STEMIs, and I wasn't sure if it was acute on chronic. It was a proximal LED lesion with an interesting angulation right at the area stenosis, and the microcatheter worked really, really well. And we just used a Minamo wire and a microcatheter, and I think got really good support, and ended up being able to cross in almost immediately. So I think that's a really good option to consider, especially in STEMIs. And obviously I'm speaking from very limited experience, but it just kind of highlights that point.
Great. So Dragos, we're missing all the CTO wires. We'll arrange, I'll have Jesse try and coordinate with you, and we'll arrange for the second part of this lecture to go through the CTO wires, okay?
Oh, sure, absolutely.
Sounds great.
Right. That was great. I hope all the fellows enjoyed it as much as I did. I really learned so much, and I appreciate you taking the time, Dragos.
Thank you so much for inviting me. I appreciate it.